Welcome to the Explainer. So, have you ever wondered how scientists or even engineers take all that messy, chaotic variation in the real world and somehow magically translate it into neat, solvable algebraic formulas? Well, today we're decoding algebraic proportion straight out of the Cambridge math syllabus. We're going to go over a super simple, foolproof method that literally works every single time. Let's dive in.
Okay, here's our game plan for today. 1. Direct versus inverse proportion. 2. The magic constant. 3. The universal 5-step method. 4. Tackling inverse proportion. And finally, 5. Mastering complex relationships.
All right, Section 1, direct versus inverse proportion.
You can actually tell whether a proportion is direct or inverse just by using a little bit of common sense. In direct proportion, both variables change in the exact same direction. If one goes up, the other goes up. If one drops, the other drops too. Pretty simple, right? But with inverse proportion, it's kind of like they're on a seesaw. When one variable goes up, the other is forced to go down.
Let's ground this with a practical example from our source material. Imagine a truck traveling a certain distance. Let's just call that X, and it uses Y liters of fuel. If you double the distance that truck travels, you are obviously going to double the amount of fuel it burns, right? They both go up. That's direct proportion for you. But now, picture a crew of X workers digging a hole in Y days. If you bring in twice as many workers to help, the time it takes to dig that hole gets cut in half. The number of workers goes up, but the days go down. That right there is the absolute essence of inverse proportion.
Moving right along to Section 2, the magic constant. So how exactly do we turn these kind of vague relationships into exact, usable math? Well, meet your new best friend, the proportionality symbol. It looks a bit like a little fish or maybe a stretched out Greek letter alpha. Whenever you see this little guy, you read it as varies as or is proportional to. So if you see the letter Y, then the symbol, then X, you'd say out loud, Y is proportional to X. It's an awesome shorthand. But there's a catch. You can't actually do algebra with a proportional to symbol. You just can't solve for it.
And that brings us to the secret key. To turn a proportion statement into an equation that we can actually solve, we do a little magic trick. We delete that proportionality symbol entirely, and we replace it with equals k. That k is what we call the constant of proportionality. Think of it as this invisible, unchanging number that perfectly links our two variables together. Once you write down equals k, you've literally unlocked the formula.
Okay, on to Section 3, the universal 5-step method.
The textbook lays out this brilliant algorithm that solves literally any proportion problem you'll ever face. Step 1, write out that proportional sign based on the word problem. Step 2, do the magic trick, replace it with equals k. Step 3, substitute your known pair of values for x and y. Step 4, use basic algebra to solve for k. And step 5, and this is the one students always seem to forget, rewrite the final formula using the exact value of k that you just found. Let's actually see this in action.
Let's walk through example 26.1 and see how this all comes together. We need to find the formula connecting x and y. So looking at the data, as x goes from 5 to 15, y goes from 3 to 9. They're both increasing, so we know for sure it's direct proportion. Step 1, write y is proportional to x. Step 2, replace that with y equals k times x. Step 3, substitute our knowns. Let's just pick the first pair where x is 5 and y is 3. So 3 equals k times 5. Step 4, solve for k, which gives us k equals 3/5. And finally, step 5, rewrite the formula. So our final perfect answer is y equals 3/5 x. See, it really is that simple.
Next up, Section 4, tackling inverse proportion.
Now, the textbook gives us a brilliant little shortcut here. When a problem tells you y is inversely proportional to x, technically you'd write y is proportional to 1 over x. But you can completely skip a mental step here. Just remember that for inverse proportion, you can jump straight to the fraction version using our magic constant k as the numerator. So you just immediately write down y equals k over x.
Let's check out example 26.2 to prove that this works. Look at the numbers. When x is 4, y is 10. But when x shoots way up to 20, y drops down to 2. One goes up, the other goes down. It's a classic inverse proportion. So we jump straight to our shortcut formula, y equals k over x. Let's substitute that first pair. 10 equals k over 4. To solve for k, we just multiply both sides by 4, giving us a magic constant of 40. So our final formula is y equals 40 over x. And we can even double check it. 40 divided by 20 definitely equals 2. I'm telling you, this method is bulletproof. Let's step it up a notch. Section 5, Mastering Complex Relationships.
So, you might be wondering, does our 5-step method hold up against more complex algebra, like squares and square roots? Spoiler alert, oh, absolutely it does. Take a look at example 26.3. The problem says, y is proportional to the square of x. Don't panic, just read it literally. Step 1, y is proportional to x squared. Step 2, y equals k times x squared. Step 3, substitute the given values, x equals 5 and y equals 10. This gives us 10 equals k times 5 squared. Now we know 5 squared is 25, right? So 10 equals 25 times k. Divide 10 by 25, simplify that fraction, and we find k equals 2/5. Step 5, rewrite. Our beautiful final formula is y equals 2/5 x squared. The system holds up perfectly.
Okay, let's do one more, the hardest one yet. Example 26.6. Y varies inversely as the square root of x. Now that sounds pretty terrifying, but let's just trust the steps. Inversely means it's going to be a fraction, and square root of x goes right on the bottom. So y equals k divided by the square root of x. We're told that when x is 4, y is 12. Let's substitute those in. 12 equals k divided by the square root of 4, while the square root of 4 is just 2. So 12 equals k over 2. Multiply by 2, and k equals 24. So our formula is y equals 24 over the square root of x. Now the question asks for y when x is 9. We just plug it in. Y equals 24 over the square root of 9. The square root of 9 is 3. 24 divided by 3 is 8. Boom! Y equals 8. We just conquered a nasty inverse square root problem without even breaking a sweat.
All right, let's bring it all together. Summary and final challenge.
Looking back at the text, here are the absolutely crucial takeaways you need to lock in. That little fish symbol means is proportional to. For direct proportion, your variables are kind of sitting on the same horizontal level, like y equals k times x squared, or k times the square root of x. But for indirect, or inverse proportion, the x variable gets shoved down into the denominator, like y equals k divided by x squared. And honestly, no matter what it looks like, your mission is always exactly the same. Substitute your knowns to find that magic constant k.
To wrap things up today, I've got a challenge for you pulled straight from question 15 in the text. The braking distance of a car is directly proportional to the square of its speed. I want you to think about the real-world physics here and think about our 5-step method. If braking distance is d and speed is s, how would you write out that starting formula? Just mentally map that out right now. Think about exactly where that k goes. If you can do that, you have officially mastered algebraic proportion. Thanks so much for joining me on this explainer today, and hey, keep looking for the math in the world around you.